Yes.
Hi and good afternoon. Welcome to the Paint Shop Track Design. My name is Fabian Robinson. Along in the team as Kyle Lindsay and Joel Escobares. Today we'll be discussing about the Paint Shop Track Design, which is basically a simple support system to withhold or withstand weight. We'll be implementing it in AAR Landing Gear Services, which is located in Medley. A background into AAR, it's a self-contained, self-sufficient aircraft landing gear service company that overhaul military, commercial, and also accessories. Our motivation was the Boeing 777 main landing gear cylinder, which is approximately 10 feet in length and about 1,300 pounds in weight. Currently, AAR cannot withhold the cylinder on the current shop track beam. And right here you can see where they're withholding the component, however it cannot be moved around the system, as well as it has an extra hoist to withhold it, so it cannot be moved by itself. Alright, this is the current paint shop that we have. They have ovens, paint booths, as well as the track beam system. The cylinder itself is taking 24 hours to actually get overhauled, well 24 hours to get painted. So with our new design, we're going to be implementing it and we'll present it more. This is a configuration of the paint booth system. Currently the paint booth system, our design alternates, we did 4 designs in total. The first 3 was actually done within the current paint booth, and the 4th was done adjacent to the paint booth. And as you can see in the first configuration, the paint booth number 2 does not have a track beam going directly to it. So Joel will explain to you more about the alternates.
Okay, as Fabian just mentioned, the current problem with the paint shop is that the track beam cannot withstand all of the products that go through the paint shop. So AAR gave us not only the flexibility to construct and design a new track beam system, but also the layout of the actual paint shop. So initially we came up with 3 different alternatives for AAR, which actually utilize the current paint shop room that is now. The problem with that is that it would, in the construction of any of these 3 alternatives, it would halt or affect production of the current system. So we came up with alternative number 4, which literally uses the space adjacent to the paint shop and will allow AAR to continue with its manufacturing and its production without affecting it, and also construct the new paint shop.
As Joel previously mentioned, we agree with AAR that the design alternate number 4 was the best for their needs. So as with any complex engineering problem, it was easiest for us to break this up into smaller sections. So we took the whole beam system and we divided it up to 29 different sections, either a straight section, a curved section, or a switch to switch between 2 different tracks. In total, we have 290 feet of track beam, 187 of which are straight sections. We have 6 48-inch switches, and we have 10 60-inch radius quarter circles. In order to support our beam system, we need to have support trusses. The support trusses are going to be placed at the center of every curved section, before and after each switch, and on the straight section so that the longest unsupported section of track is no longer than 12 feet. Each support truss consists of a crossbeam on the top and 2 vertical supports. We have 27 support trusses, so we have 54 vertical supports. The first step in our track beam analysis was to determine a design factor. The design factor is important to account for larger pieces that they may encounter in the future, as well for any unaccounted for forces that we may have simplified. It really depends on the purpose of the system and is ultimately up to the owner's specification. We agree with AAR to use a design factor of 4.0 for our design. The next step was to determine the total vertical load that we expect our system to be experiencing on a single 12-foot unsupported section. So we took the weight of the heaviest component, which is 1,300 pounds. We multiply that by our design factor. We also include the weight of 2 trolleys and the weight of any hardware hooks or slings that are associated with that. We estimate to be 20 pounds. In calculating the total vertical force, we also need to include the weight of the beam. The beam has a weight in itself. The beam that we ended up choosing is 16 pounds per feet. So here we add the 16 pounds per foot times the 12 feet, and we get a total vertical force of 5,448 pounds. Once we have the total vertical force, we can calculate the maximum shear force, which was plus or minus 2,724 pounds. We can also calculate the maximum bending moment, which was 16,056 pound-feet. Once we have the maximum bending moment calculated, we can plug it into these equations here to calculate the actual stresses on the beam in both the X and the Y direction. Once these are calculated, we need to figure out the allowable stresses. The Crane Manufacturers Association of America provides these guidelines for compression, tension, shear, and bearing stress based on the yield strength of the material. All the beams that we analyzed are A992 steel, so the yield strength is 60 KSI, so that gives you these values here for allowable stresses. The next step is then to then compare the actual stresses to the allowable stresses. So we do that in both the X and the Y direction, and we make sure that this value remains equal or less than 1. We also calculated a combined stress ratio where we add both of these ratios together, the X direction and the Y direction, and we want to make sure again that this remains less than or equal to 1. Our next step was to check the vertical deflection of the beam. In checking the deflection, we need to include, like I said before, the weight of the beam and also the load that's going to be applied at the midspan. So the first term here is for the weight of the beam. This term is for the applied load. And as per CMAA, it's important that this remain less than the total unbraced length divided by 450. In our case, since that's 12 feet, that gives us 0.32 inches of maximum allowable deflection. Due to the fact that the trolley wheels are applied on the bottom flange of the I-beam, it's very important to also check for local flange bending. We can use these equations provided by the Crane Manufacturers Association of America to check at 3 critical points as shown in the picture here. Once we calculate the stresses, we can calculate the resultant biaxial stress at each point, and it's important that this value remain less than or equal to 66% of the yield strength, which in our case would be 33 KSI. So we performed this track beam analysis on all standard and wide flange I-beams available on the U.S. market. All these I-beams come in A992 carbon steel. Since these prices for these beams are really determined by the amount of material that goes into the beam, because they're standard beams, the first beam the beam with the smallest cross-sectional area that satisfies all previous conditions that I mentioned would be the most economical beam for our design. In our case, that's the W6x16, so it means it's a wide flange I-beam. It's about 6 inches tall and it's 16 pounds per feet. We actually have a 6-inch section of it right here.
Okay, so then after we did all this calculation to get the lateral and horizontal load, we had to do the support column analysis. And doing the support column analysis, there will be movement to the part. So we had to do a dynamic load analysis. We took in consideration the dead load factor, the dead load, the trolley load, as well as the lifted load. And we used an eccentric column loading secant using the secant formula. We selected the hollow HSS support tube. The HSS support tube has an ASTM 500C, which has a KSI of 50,000 PSI. With that, after using the secant formula, we selected the 4x4 by a half, which is giving us a PSI, a PLO of 67,532. As you can see here, this is actually what the SolidWorks simulation did, and we'll go into further details.
Okay, now since this is a self-supporting system, we wanted to add to the rigidity of the system in any way possible. So we decided to add gusset plates and base plates to the design. In doing so, we followed the LRFD method, which is the load and resistance factor design method given by AISC, the American Institute of Steel Construction. We use the rules of thumb given by them, which give a haunch length of at least 10% of the overhead beam length. For us, the overhead beam length will be 108 inches, so 10% of that is 10.8. Our design has a 20-inch haunch length, which is well within the guidelines. The haunch depth is required to be at least 2% of the overhead beam length, which theoretically will be 2.2 inches, and our actual design is 10 inches, so that as well gives within guidelines. For the base plate, we use these given equations by the AISC, and we use that to determine the dimensions of the base plates.
So we had to do a prototype due to the fact that codes such as Miami-Dade codes are going to prevent us from implementing the system. So therefore, we did 2 prototypes. We did a 1 to 12 prototype, which you can see here. This is actually just displaying exactly how it will look, or the support of it, a section, or unsupported section. We did a 1 to 6, which we tested with the 1:6 scale, we did a 320 pounds, which is equivalent to 1,477 pounds. On the trap beam system, we did 24 inches. This trap beam system is actually 24 inches, which simulates the 12-foot unsupported length. The cross beam, which is this section right here, 18 inches, which supported the 9-foot length, and 8.5 foot, which is the support, and the gasket plates right here, and then also the base plates. After doing that, we did the point loads. And the point loads, we did 4 different point loads. We did 4 different sections. First, you can see this is in the mid-span. We did a 4.5 inches from the mid-span, get a maximum deflection of 0.125. This section, you can see we actually did a 1 from the center, and 1 inch from the center, and 3 inches from the crossbeam, giving us 0.0625. The other 2 sections, which is directly below the crossbeam, and also 5 inches from the crossbeam, gave us values way below because we're using tape measures. Good. Simulation, the SolidWorks simulation, what we did for this section actually said that a maximum deflection would be 0.110. And after we selected every single thing, such as did the testing, we also did the selection for the support tubes, the support sections. We did a final cost estimate. Being that we had to do for the complete paint shop, we had to do air preparation for the section that is going to be used. We had to remove, for instance, the hazmat room needs to be removed. There is a computer server that needs to be removed and demolition of the storage closet, which is going to give us a price of about $48,000. Materials such as the paint booth, the trap beam, the cross beam, support oven lamps for the oven will be about $277,000. Fees such as general contractor, engineering fees, due to the fact that we are not legally signed, we cannot sign off anything, we have to get an engineer, is going to run with contingency 104, giving a grand total of about $480,000. But we estimate with contingency, we did it at a price of 10%. So if in case of anything that might show up, it will cover due to the material and the air preparation. It's estimated that we'll have this done within, or the paint shop will pay back for itself within 6 years due to the fact that if AER received 10 support systems, if AER received 10 ship set of 777, they will save 48 man hours per ship, per gear, per component, which is going to pay off back for itself for $480,000.
Okay, as with any engineering, major engineering project, we are going to take into consider any challenges. These are a list of challenges that we took into consideration. Most notably was safety. In our design, we implemented it so as any paint removal or any scuffing is taken away from the actual paint booths. So any safety for hazmat areas or spray is taken into consideration. Also, for any workers at AAR, we took into consideration that the system has to support itself no matter what. So the safety of the workers is taken. And also, the final product of this AAR facility is the landing gear systems. So any customers of any flight, commercial flights will be taken into consideration and dealt with here. This is a list of organizations that we use standards from. Most notably was the American Institute of Steel Construction, or AISC, and also the Crane Manufacturers Association of America, CMAA. Those two really gave us the most guidance and guidelines in our project. Team responsibilities, we each were responsible for our own division of the project, but we worked as a team as well, and we helped each other out and finally got the project completed successfully. The timeline, we generally stayed on time with everything that we were supposed to complete, and we have presented to AAR, and they're in accordance with our project. Global learning, AAR has a similar facility in Malaysia, so we believe that they can use this design and this layout for any purpose that they deem necessary. So we believe that they can use this in Malaysia as well. Also, safety. We did come up with a bilingual safety manual for the tracking system in English and Spanish, which are the 2 predominant languages in South Florida. And in conclusion, we will allow AAR to safely and efficiently move next generation of larger airplane components through the paint shop, and any future work take in consideration air circulation, the thermal efficiency of lamps and ovens, and among any other components deemed necessary. And that concludes our presentation. Any questions?
Yeah, you did a simulation of the straight section of beam. Have you done any simulation of the bends?
No, we did not do simulations of the bends because we decided that we were going to support every bend in the center of the bend. And since it's only a 5-foot radius, that the 12-foot unsupported section would be much more likely to fail than that.
Did you calculate like floor anchoring, your
Yes, we did.
concrete,
For the base plate,
your
we did
rebar?
concrete stress, which we did.
46 inches.
Correct. There's a 14 inches concrete that is actually there. We did a stress analysis for the bolts, the anchors that had to be used, and also for the base plate. Due to the fact of the size of the base plate
Right.
and the support, yes, we did.
Okay.
And also the design of the base plates is more theoretical than analytical. So as I mentioned, the LRFD method, which is given by AIC, it's more designed on the dimensions of the actual plate instead of load or going off of that.
Yes, ma'am.
Before you got this project, had you ever seen a paint shop track beam system?
Yes, I actually did because I currently work there.
Oh.
Yeah, he works there. Honestly, I had no idea what it was when he told me that, I got the project for us is the paint shop track beam. I had to go there and see it myself.
From scratch for YouTube, but
Correct. Yes.
That's why we really wanted to just bring a small section, even though it's not, scale and strength, at least it's scale and size, just so you can get an idea of what we're talking about here.
Yeah, we learned a lot. It seems very simple, but there's a lot of work that goes into it.
The design that you guys are proposing, is it saving them in time as far as from start to finish when they bring in the landing gear and then they ship it out to be mounted on the...
Correct. So you're limited to the CMM, being that you can only do a certain amount of primer, the thickness of the primer, and also the time of the oven.
Right.
However, due to the fact that they cannot put it through the ovens, they have to leave it outside to have the paint cured for 24 hours.
Right.
So when you actually have the track beam system running through the ovens, you can have the larger components go into the oven, and within 3 hours it's completed.
So
it's saving a lot of time,
A lot of
yes.
time, I see. Which is a win-win.
Correct. So it's like a total of like 40 hours per ship set, and it's 2 main cylinder per ship set.
I don't know if you guys know the answers, roughly how many, say that particular landing gear that you guys, this was in 777,
Correct.
roughly in a week's, how many of those did you do a week roughly?
Okay, so currently you can do both. They're currently doing 1 per month,
Okay.
but as being that the fact that it's 10 years or 20,000 cycles, we're now in the area that all 777s are going for overhaul, so
Right.
it's going to ramp up soon.
I see. So they're getting ready for that?
Yes, that's correct.
So my question actually, as a follow-up to that then, is have you considered scalability? As now that you've improved their process, you've improved their efficiency, have you left them with the ability to add another paint booth or add another track system to integrate and further scale that system?
Right. So they're limited to space. So that was a major engineering issue that we had. So the first, as you see, the first designs, we did it within the current paint shop. It was going to prevent production.
Right.
So they only had one section outside. That's where you're going to actually do a preparation to remove all that section and put a paint shop. So you kind of limited the space as future growth.
What I'm saying is it scalable then to maybe inside to the current paint shop that they wouldn't have to necessarily demolish or repurpose it, but they could actually integrate it into the new setup?
Yes.
Yes, definitely. We actually have a beam section. See this one? This is inside the current paint booth room, and there's a wall here that separates it. This is the scuffing area, so it doesn't contaminate the painting area as well. So all of this area is the current paint shop right now. So if they deem necessary that they wanted to use that or whatever they want to do, it's up to them.
Quick question also in terms of scalability. If I take that process, generally speaking, based on your learning experience, can we take this and use an equivalent airplane like Airbus 340, for example?
Yes. Airbus 340, the
With the
landing gear
same-
components. Landing gear, if you're going to A340, however, this is not scaled for a complete airplane, or however, landing gears, yes. So you can do, currently they have A340, A380, the whole Airbus fleet, and
Right.
going forward, they're actually going to A350, which is actually a small, they're going more fuel efficient, so they're going smaller components, lighter weight. But this is currently the largest on the market.
Correct.
Is there a return on investment concern being 6 years instead of like 1.5 years or 2 years?
They didn't mention that they needed to get it done immediately, and due to the fact that we're estimating it at 1 shipment per month, and it hasn't ramped up as yet, it's actually going to be done in less than 6 years.
The cost that you've listed there, close to $478,000, how close is that to the estimate that the AAR was willing to put out?
Well, we provided this to AAR, and they were 100% with it. They were expecting $600,000 and some thousand dollars due to the fact that they're doing their plating shop, but due to the fact that plating shop has to do with more chemicals, there are more fees.
I have one other comment. I mean, you're looking at 48,000, 277,000, and then is that $104 for
$104,000.
Oh. Oh. I was gonna say, you really undersold yourself. I'm sorry, I don't have my glasses.
No problem.
Yeah, we noticed.
Any other questions?
Well, thank you very much.
Next, we have Senior Design Team 17, and their project is on the SAE Formula Race engine development.